Hello and welcome back to another video with It's Dr. Dan. And today the whole entire goal is to go through how to fill in molecular orbital diagrams. So what we're going to be doing is we're going to go through some of the basic ideas of how this works. We're going to be learning how to predict when something's paramagnetic, diamagnetic, how to fill in bond order, and how to count our bonding and anti-bonding. So as we go through this, the whole idea here is that it's exactly like electron configuration. We're going to be following the Aufbau principle, Hund's rule, and the Pauli exclusion principle. Same ideas that you would before, but instead with the molecular orbital picture instead. So it allows us to predict all those different properties. So when we're going to go through this, now depending on your professor or who you're learning from, all of them are a little bit different. So sometimes they'll give you the orbitals and you just got to fill them in and do your calculations. Others can be a little different and be harder, and you have to be able to predict them and know the actual understanding behind it. Typically depends on what level of course you're in. So for example, my general chemistry courses, I usually always give the diagrams and they just have to fill it in. So we're going to look at the bonding, anti-bonding orbitals and use that to be able to determine what the bond strength is, which allows us to figure out what is the bond order. Now with bond order, it's just an equation. All we're doing is counting, well, how many electrons are in the bonding orbitals, right? So the ones without stars. And then we're subtracting it from the anti-bonding orbitals, so the ones with stars, okay? So that's all we're doing is no stars minus stars divided by 2. Now, this is where some of the bond order numbers came from before. It's the true reason where it comes from. So it's single bonds are always 1, double bonds are 2, triple bonds are 3. If it can't bond, that's a 0. And if you ever see a non-integer number, that's typically meaning that it could have resonance behind it, for especially if you think of like really large structures, or it's telling you that the bond is weakened or stronger. So, like for example, if you have a 3, like that's probably your strongest bond, being it's a triple bond, or for most normal molecules. But if you have like a 2.5, that's telling you it's a little weaker than 3. So the strongest in this for most cases is going to be 3. The weakest is going to be, 1 or zero point 0.5 if you can get a zero point 0.5. So it's always it's a scale when we're talking about energy. All right. So that's what we're going to try to do as we go through these examples. So let's take a look. So the first thing is when we're trying to go through these examples is how exactly do the orbitals work? Well, if you remember from my previous video, it was all about if you have 2 atomic orbitals going in, you're going to get 2 molecular orbitals coming out. So generally the way that we end up kind of looking at this is that the 2 orbitals are going to try to combine with each other. But as a result, the whole idea here was, well, the phases of the orbitals, they're going to both construct and deconstruct. So meaning it is going to split into essentially 2 different molecular orbitals as a result of these interacting with one another. So what kind of orbitals, what would we make? Well, if we have, let's say, an S orbital and an S orbital coming together, well, what can we kind of predict? Well, we see overlap between both of them. So what does that mean? Is we're going to have a sigma orbital for both. So the lower energy is going to be your bonding orbital, and then the higher is your anti-bonding. So that's when we put the little star, just to say that, hey, this is higher in energy. So it's going off of what we talked about before. Now, this is where we take the electrons from our valence for each atom. So we have the one on the right, and then we also have the one on the left as well. And we're just going to fill them into the middle. So we're going to fill them in from the bottom first. So I'm going to take 1 electron from the hydrogen on the left, and then we'll fill in 1 from the one on the right. So how about this? We'll do a different color for it. So essentially, they're both going to end up filling in from each side, and it's going to be creating a molecular orbital between it. So there's a couple questions we can end up answering here. So the first one is bond order. Okay, so the whole idea of bond order is we're counting bonding electrons, minusing it from anti-bonding, dividing by 2. Well, in this one, right, if we were to look at our orbital that is filled at the moment, well, the only thing here is that we have how many bonding electrons? Well, we got 2, right? So there's 2 in bonding. Now, how many of them are in anti-bonding? Well, if we look closely, we see a whole lot of nothing, right? So what is the math going to be there? 2 minus 0 divided by 2 is going to be equal to a bond order of 1. which does that make sense? Well, if you were to draw the Lewis structure, it's H single bonded to H. So yeah, that's great. So hey, it works. We like that. All right, now is it paramagnetic or diamagnetic? Well, diamagnetic was all about if everything is paired up, it would be diamagnetic, which it is. So hydrogen gas is not magnetic. Oh, sad days. That's okay. All right, now the next part is molecular electron configuration, which is a little different. But it's similar to electron configuration, where if you remember, you did like 1s2, 2s2, 2p6. The only difference here is you're counting what's in each of those orbitals. So, for example, our first orbital was sigma 1s, and we're counting how many electrons we have in there, which is a total of 2, right? And if we had more, we would fill them all in as well. So that's just our first one, and that's it. Let's do another one, right? Let's keep trying to fill this in. All right, so for this one, we got helium and helium connecting together. So two noble gases, can they bond together? Let's try to take a look. So the whole idea, right? We have our sigma orbitals already labeled in, right? Two atomic orbitals, the 1s and 1s go in, and it should be two molecular orbitals come out. So all we're going to do is we're going to take one electron from the left, we're going to take one from the right, and we're going to take another one from the left, and another one from the right, combine them all together. And what do we got? We got two in the anti-bonding, two in the bonding. So how do we do our math? Well, it's going to be 2 minus 2 divided by 2. So as a result, it's going to probably be very undefined or 0. So what does that mean is that we do not have a bond that makes. And that should make sense, right? Noble gases, they don't want to interact with each other. They generally only do dispersion forces. They can't do much else. So our bond order in this case is going to be 0. Now, is it diamagnetic or paramagnetic? Once again, we still do not have any unpaired electrons. So it's going to be diamagnetic again. Helium is not magnetic. So if we were going to fill in our electron configuration, well, we're going through all the orbitals we have. We had sigma 1s, and then we also had sigma 1s with that's anti-bonding with a little star. So now we're going to fill in how many electrons we have in each. So we got 2 in the first one, 2 in the second one. And we're just kind of summarizing this big diagram that's up there. That's the whole idea. Let's do the next diatomic that could form based on the periodic table. Let's see what else is possible. Okay, so lithium 2. We're moving up the periodic table, meaning we're on the second valence level, meaning we have one valence electron for each of the different elements that are here. So we got 1 and 2s for each of the elements. So we're going to combine them both together. So one's coming from the lithium on the left, the other one's going to come from the lithium on the other side. So if we're going to calculate our bond order, all we're going to do is it's 2 in the 2 in the bonding, 0 in the anti-bonding, divide by 2. So what do we get is a bond order of 1, so it should be a single bond. Hey, it's following our bond trends. And that makes sense. So this is where the bond trends or properties are coming from. Not just something that scientists are like, hey, student, memorize, right? No, it's actually coming from somewhere as we're kind of going through it. It's going to be diamagnetic, once again, because we still don't have anything paired up. Now, if we were going to try to summarize this, right now we're in sigma 2s, and we have a total of 2 electrons in here. Depending on, you can summarize it even to include the 1s from before. So that is something that you could include everything as like a more of a complete notation as well. So based on this diagram, we just have sigma 2s. But if you want to be thorough about it, you could say sigma 1s2, sigma 1s star 2. So taking the helium part and then combining it with our lithium here. So bringing in all the different orbitals, all the MO orbitals that are interacting. All right, can beryllium 2 exist if we were to go through this one? All right, so first is if we were to fill in our electrons for our valence level, we have 2 valence electrons for beryllium, right? Checking your periodic table, second column. So if we're to fill in these electrons, we're going to be giving 2 electrons from each atom into both orbitals. So once again, if we were to do the math here, we can see 2 in the bonding on the bottom, 2 in the anti-bonding on the top, and we're dividing that by the 2 nuclei, right, that are here. So what do we got? We got a big old 0. So what does that mean? That means no bond that's going to be super unstable. It's not going to happen. right? So no bond is going to be being made here. It's unstable, is what that says. So as a result, being that there's no bond, generally we wouldn't assign diamagnetic or paramagnetic, but based off what we have there, might as well be thorough. It would be diamagnetic. And in terms of our electron configuration, this one, I would really pay attention to what every teacher does. Sometimes they will include the 1s like I did on the example before. Some will just only go off of what you have here. Usually I'm okay with you just going off what's being shown in the diagram. So, but everybody's a little different, depends on how much you have. So we would have sigma 2s2, and then sigma 2s with a star with a 2. And keep in mind, if you had to do the entire thing, you would add the configuration for 1s and 1s antibonding with a star on it, and you'd have all of them. One other thing to kind of keep in mind, everybody does teach us sometimes different. Some people don't use a sigma symbol as well. So as I'm kind of reading about this and checking different textbooks just to be thorough, I do sometimes see that people will use just the letter S, not for the s orbital, but for sigma. So keep that in mind if anyone ever sees like sigma 2s2 or s2s star 2, it's referring to sigma. So it's just another way. Same with pi using a p. So it's another way that it can be written for these different structures. So keep that in mind if you're someone that's like, I don't recognize any of this. It's just another way of viewing it. Right? Let's look at another one. All right, with boron, this is where it starts getting more complicated. Typically with MO theory, we don't usually go above neon 2, which is like on that second row. Being that on the third level, that's when you get access to the d orbitals, and it gets really complicated where you really would probably need the help with advanced computing to figure out all the diatomic elements and exactly what do they look like. So the first thing just to point out, right, you can see the 2s is exactly the same. So if we were doing boron 2, well, we would fill in our valence electrons just like we would before, right? So there's 3 valence electrons. So we're going to fill in those different valence electrons here. So when we're doing this one, the bottom one, let's do that real quick, being that's just following our normal thing, right? We see that everything's going to be filled up. So when you have atomic orbitals filled, you kind of might be noticing the trend is that the molecular orbitals are going to be filled too. Now, when we get to the p block, that's when it gets a little harder. And the big thing is, well, it's because there was more possible. You had 6 electrons that were there. So if you think the hybridization, well, what could you make with the p block? Is that, well, what's possible is you could always have a sigma, a pi, and a pi that are always going to be possible with each of those orbitals that are there. So you always make 1 sigma and then 2 pi's. So if we're to go through this, well, the first thing is that the pi orbitals end up being lower in energy at first for the first 3 elements in the p block. So for boron, uh, for carbon and nitrogen, they're all lower. And the whole reason for that was if you remember, for electron configuration, you filled 1 electron in its own room all by itself in the electron configuration. So it was way happier as a result. So with this one, we're going to actually have 1 in each of its own little orbitals that are here. And what are they? Well, essentially, we're going to have 5, or sorry, not 5, pi py, and then pi pz. And now the reason why you have both is that they're both parallel no matter what direction. They're degenerate, meaning they're equivalent to one another, okay? So it's kind of going off your electron configuration where they're all the same. The only one that's a little bit different is the sigma px orbital, or sorry, I should put a 2px and 2py for all these, is the sigma bond actually ends up being a little bit lower in energy or higher in energy for these first 3 elements. And then we'll kind of continue saying, okay, we have sigma star 2py, or pi 2py star, and then pi star 2pz. And then we have sigma 2pz, also with a star. So we have the anti-bonding all the way at the top, the bonding at the bottom. So we filled in those lonely electrons at the bottom. So we're trying to calculate our bond order. What are we going to do is we're going to, once again, count all the bonding orbitals. So we would have 2 in the sigma 2s. Then we'd have another 2 in the pi group. So what would that be? Is that it's going to be 4. And then we have 2 in the anti-bonding, so with the little stars. So it'd be 4 minus 2. So we're just looking for the stars. It's kind of one way to look through it. We're going to divide that by 2. So what is that going to be? It's going to be 2 divided by 2, and that's going to be a bond order of 1. So between boron and boron, we can only make a single bond. If we were trying to connect these guys together, would be the entire idea here. So in terms of, is this one diamagnetic or paramagnetic? Well, we actually have lonely electrons for the first time up in the top. So what would that mean is that, well, if you had diboron, this would actually be paramagnetic. So it would be something that could be magnetized. So if we were to trying to fill in our orbitals, so we have sigma 2s, 2 of them in there. We have sigma 2s star, 2 of them in there. And then the next one, how do we do these pi ones? Well, we'd say pi 2py, comma, pi 2pz, and an end parentheses. And the reason why we're doing that is because they are equivalent all the way up to the top there. So what we're doing is we're just going to say that, hey, we got 2 electrons in there, and it can fit a total of 4. So that can go up a lot higher because we're talking about 2 orbitals. So every orbital can hold 2 electrons. So we'd have more electrons that can go in there. All right, so our last one's going to be all about oxygen. So with this one, it's going to be a little bit different than what we were seeing before. You can see that if you kind of remember the order of how you might have wrote down the orbitals actually changes with the structure. So this is where we start seeing sp mixing happening, and this was actually occurring on the previous orbitals too. I just didn't mention it yet. And it's all because of how the electron configuration is filled in for oxygen. So if you can think of the valence level, so let's say if we did the one on the left, so we had the 2 in S, and then we would fill in P. Now, when we were talking about like boron, nitrogen, and carbon, we would fill all the way across and everything had its own bedroom, right? When it came to all the individual electrons that are there. So with that entire idea there, everything having its own own little room, it would cause actually a want to do more pi bonding versus doing sigma bonding. But now that we have this extra electron here, it now wants to do sigma bonding. So the orbital moved down. So we can see the sigma 2px is actually lower in energy, and then the pi orbitals are actually now in the middle. So if we were to fill this in, right, so we'll put the other oxygen on the right here. So filling in all of our electrons. What we're going to do is we'll fill in everything from in the sigma area, or sorry, not the sigma 2s area. We see that completely cancels out. Everything's filled up. Now we're going to fill in all of our electrons in each orbital from our left atom, and then we'll fill in all of them for the right as well. So once we do that, we can see that, okay, we have all 6 electrons for blue, all 6 electrons for red, I think. Or it should be everything. 1, 2, 3, 4, 5, 6. Yeah, so we have, 3, 2, 1. So we have all the electrons accounted for here. So we got all 6 on both sides. So that's great. Now, the one thing to point out is, oh, up top, you actually have some unpaired electrons that are here, which if you remember, if you watched my previous video about this, was all about that. Hey, if we have this oxygen here, is that we should actually be able to see this magnetic property. So if I'm going to fast forward here and I pour oxygen between the 2 magnets, we're going to see oxygen getting stuck between the poles, and that's because of those electrons. So there are 2 unpaired electrons. It's just in the molecular orbitals where it is. Who would have thought? So it's just a little bit more complicated, right, than anything that we normally look at, but it is something that it is actually there. So if we were trying to go through our math here, so doing bond order, so how many bond orders do we have? So let's see, we got 1, we got 2, then we have 3 and 4, then we got 5, 6, 7, 8. So we have 8. Then for anti-bonding, we have 2. Then we have 3 and 4. So it'd be 8 minus 4 divided by 2. And what does that tell us? Is that we'll have a bond order of 2, which backs up our double bonded Lewis structure. So it helps tell us that, yes, we have a double bond. We can prove it with the theory. Then we could fill in everything else, right? We know it's paramagnetic because we're seeing the magnetization. We were able to observe it. We can explain the result. Now we could fill in all of our orbitals. So we had sigma 2s2, sigma 2s star 2. Then we had sigma 2px 2. And then we had pi 2py, pi 2pz. So if you keep in mind, that one was where we did pi 2py, pi 2pz, and that would be a 4. And that's referring to these 4 electrons right here. And then we'll have the pi 2py, pi 2pz 2, because there's only 2 electrons. So let's kind of move all this over a little bit and make some room, and that will be our last one. So this is something that it is quite a lot, right, to try to wrap our heads around, but it is totally manageable. It's just another way of doing electron configuration. So just to end this, right, question for you, right, is think of what bond order does N2 have, and and after you draw the orbitals, is it para or is it diamagnetic, or for N2? So could you do that? So if you're my student, that's gonna be your question that's about to pop up. And if you are watching this video, feel free to put your answer down in the comment section, what you think it is, and I'll tell you if it's right or wrong. All right, thank you so much for watching, and I appreciate you, and I hope you have a wonderful rest of your day. Bye now.